Okay. So today we will be covering the theoretical aspect of what we have been discussing so far in the previous classes. Um, as you may remember, we covered an end-to-end learning um, steps using a Jupyter notebook for, I believe, the 3 classes in the past. And then before that, we discussed about the required Python settings or libraries that are important, mainly like the NumPy, the Panda, and the Matplotlib. Those 3 libraries, and on top of that, we discussed about code that basically shows the end-to-end machine learning process. And in the process, we did go through how we can just load the data, transform the data, and do some data splitting for training and testing purposes while training a machine learning model. Now, as I promised, today we will be covering the theoretical aspect of this, and I will be very fast going through the theories. And just as you can see from the title, we are going to discuss about the supervised and unsupervised machine learning, and some unsupervised machine learning algorithms and unsupervised machine learning algorithms, how we can measure those matrices. Yeah, I may have to switch the display and also the share. Let me quickly stop the share and switch the display. And again, share. Okay. Now we are here. Okay. And thank you for joining. So I know just we know what machine learning is, but I want to start from the basics so that it gives us enough context about the supervised and unsupervised machine learning. And machine learning is a discipline that focuses on the creation of algorithms to allow machines or computers to learn from data. And the technique of data analytics in statistics and machine learning are kind of the same, but for different applications. In just machine learning, we use models for prediction, whereas in statistics, we use models for estimation and with a certain confidence interval. So linear and logistic regression models are common for machine learning and statistics, and just they are used for different purposes, both in statistics and machine learning. So due to the application differences in machine learning and statistics, models design and development workflows are a little different. So from machine learning perspective, we have this experimental design in constructing the inputs. And the EDA means explorative data analytics process is part of the machine learning design workflow, where you involve, if you remember from our discussion last time, you start with a problem statement or a business understanding where you have a certain problem that you want to target to solve. So you have a business problem or a problem statement, and then just you will have data, and from this data, you get extract certain features that help you to understand or help you solve the problem at hand. And the process of getting your machine learning, your data and extracting features and aligning those features to address or answer the problem statement at hand is a machine learning process. And finally, you will generate a predictive model, depending upon the type of machine learning, whether it is supervised or unsupervised process, you will ultimately get a model. And then let's closely look at the process, the problem statement, and this is a practical scenario. If you would have a problem statement, and now the outcome features will be identified, and then just the EDA process involves feature engineering. You may have to create new features that didn't exist in the data by doing additional mathematical operations on the existing features. You could create new features by transforming the features by using some different mathematical techniques. For example, logarithm, the natural logarithm. If you remember, we used a natural logarithm to transform certain data in the California business, the California housing data. So transforming features that are in different scales improves model performance. And scaling types involve logarithm, the min max, or the mean. Transformations or scaling enable us to scale the data so that we can normalize the data. So this is like just the pre-processing process. Remember, we did this in the end-to-end data machine learning process. And pre-processing is done on input data, and it should be done on the new data too. Just whatever pre-processing that we do for machine learning model training, we should properly document and remember the steps, the specific detailed steps that we used when transforming the data for training the model, because the data comes naturally in the exact way as we used that we processed. Right, so we need to do exactly the same pre-processing on the new data that we are going to utilize the model on. So pre-processing that you do on the input data that you use for model training should be applied on the new data or in just the future data. So documentation is important, or if you have written a code, obviously that's the process. You have to keep the code that you used to transform the data for machine learning training purpose, because once the model is trained, then the new data, which comes in a natural form as the data that you pre-processed for the model training purpose, requires pre-processing. So the new data requires pre-processing. That pre-processing step, the pre-processing step should be exactly the same as the one that you used for the model training process. So training and testing data split is done for training the target model and then simulating the future. When you have a model just for machine learning model training, you would have to split. And just you remember we did that. We did 80-20 data split in the end-to-end code that we were executing over the last 2 or 3 weeks. And then the testing and training data split should be 70-30 or 75-25, depending upon the size. And the feature engineering, we covered the input data, the data pre-processing, and finally you have the training set and the testing set. By the way, remember, there are different approaches. There are different people approach this differently. But my suggestion, my advice for machine learning process is do the data pre-processing both on the entire data that before splitting the data into training set and testing set. Before splitting the data, do the pre-processing. The data pre-processing logic or the steps that you used for this step should be kept. If it is a code, keep it, and then just you will use it later in the future once you got the model. And to improve performance, for example, a model now. For example, like just let's say we have a data that we use to predict the burn area. This is like just most common in the US, and then most common in US in Canada. In US in Canada, it's most common to have forest fire. And forest fire gets happens usually like just during summer. So to calculate the forest fire area, the area that would be impacted by a forest, we use data. So we use data, and this data has got different attributes. And one of the attributes could be the temperature, as during summer. Also in Ethiopia, summer is considered as the rainy season in Ethiopia. In US and Canada, summer is the hottest season in this part of the world. So temperature will rise, and just the peak of the temperature in this area will be during summer. So at this time, when the temperature goes high, the forest climate changes, and as a result of that, with high temperature, the burn area would potentially be high. In any case, so this is an example used taken from that kind of data. And now, so you can have a linear regression or a model that basically enables you to predict the burn area based on the temperature of the time. And now to do that, you divide the training set into k-fold. Now, just this is basically a k-fold means this is one of the approaches of machine learning. When you do a machine learning process, you may simply just train your data. You may simply use the training data in just in one shot, or you may split your training data into k splits. K could be 10 or less than that or more than that. But just when we say k folds, that means we are dividing our data set into the training part. Remember, like just this is the pre-processed data, which is split into this training set, let's say, which is 80% of the data, and this testing set, which is 20% of, or depending upon the size, 20% when this is 80, 25% when this is 75, 30% when this side is 70%. So 30% when this side is 70%. In any case, whatever portion that we kept for the training data has to be split into k folds, and then just we use all the k minus 1 folds and just the k's data set and do multiple iteration. So that enables us to evaluate the model's predictive accuracy in each cross-validation run. We call this kind of run as a cross-validation. The cross-validation is you take k minus 1 of the portions to train, even within the training, and the k's portion, or just the one portion that you have out of k portions for testing, and then just you evaluate iterate so you do that k times, and then just you compare the different models using different prediction accuracy metrics, such as mean absolute error or root mean square error. So these are some of the accuracy metrics that we could use during the training process, and also during the after the training process, we could use the testing data set on the trained model. In any case, so this is a cross-validation approach. And when we want to evaluate the accuracy or the predictive accuracy of models, we could use the mean absolute error, which I mentioned in the earlier slide. And the mean absolute error is nothing but the mean of, look, this is a predicted value. The model is used to predict a value, right? And also, especially in supervised machine learning, we will have observed data, and then we let the model to predict. So we calculate the difference between the predicted and the observed value for each data point that we used to evaluate the model on, especially just the 25% or the 20%, the testing portion, the 25, the 20, 25 or 30% of the data set will have as many data points. So for each data point, we calculate, we use the model to capture the predicted data, and also each data point will have its own observed data, and the difference will be used for the mean absolute error. So I think this formula is wrong. I have to fix it. This is not right. Not the mean. Give me one moment. This has to be corrected. This is not a square. Okay, it's not square. The mean absolute error is the absolute value of the numbers, the difference. So this is what it is. The predicted minus the observed, the absolute value, and then just the sum of all those divided by the number of observations that we used for testing the model. So this n is the number of observations in the testing portion, and the root mean square is exactly the same but a little different. This is the square of the previous one, and then just the root mean square. So finally, based on the evaluation, we pick the right model, which gives us a good performance or a better measure. The mean absolute error or the root mean square error will enable us to compare multiple models, especially like just if you see here in the cross validation within the training process. We let the algorithm to use the mean absolute error and the root mean square error, and then just pick the one with the smallest value, the smallest mean absolute error, because this is about the errors. The smallest mean absolute error or the smallest root mean square error will be the best model of all the models that we evaluated, especially just because each cross validation generates a model and a corresponding root mean square and mean absolute error. So now there is one important thing that we need to take into account. At times, our model would work so good during the training process, so good, like just and then just whether we calculate mean absolute error or root mean square error, it gives a very good performance, And unfortunately, at times we may run into situations where the testing performance will be lower than the training performance, because in the training performance we calculate, we let the model to be trained and then to be calculated against the predicted and the observed value, especially just when we have cross validations, k-fold cross validations. In that case, the model is said to be overfit. If the model is not up to the expectation on the test data, if the performance of the model during training is better than the performance of the model during testing, that means the model is overfitting. Overfitting. It's just it understood the training data but didn't do well, is not doing well. Underfitting means it didn't do well during the training process, but it shows a good performance in the testing. So we have to strike the balance between the underfitting and overfitting. So to do that, we have approach, and just the variance and bias are some of the measures. Variance captures how much the model changes if the training, if you train on a different training set. So how over specialized is your model to a particular training set, which is overfitting, which means we let the model to train on a certain data and then just try it on a testing data. So if it's simply over specialized on the training data, that means your model is on overfit. And bias is measures what the error that we obtain from our model even with infinite training data. So this is due to a model being biased to a particular kind of solution, or let's say a linear classifier. In other words, bias is inherent to the model that we basically just utilize. Overfitting and underfitting can be just seen like this. Overfitting is a high variance with low bias, a model which is optimized to a training data and cannot generalize on unseen data is overfit. And typically of overly complicated models with too many features and overcomplicated algorithms structure would result in overfitting. And underfitting is with low variance and high bias, which happens on overgeneralized and which on models that cannot model complex behavior. So most of the time, like just in linear regression, this kind of scenario happens because linear regression cannot model a complex behavior, and which we will quickly see. So this graph shows us how a high error, this is a high error, and this is a complex classification process, and this is a simpler classifier. Then just as the classifier goes more and more, although we minimize the error, but the bias would increase. And the error slash loss on an unseen data set could happen, like just if it is too complex. For too simple, higher error. For too complex, a lower error, but there would be a bias. And we discussed about pre-processing, and in pre-processing, we do models should be tested on data not included in the training. The model can memorize rather than generalize, which means overfitting. If by accident you use both the testing and the training data together and assumed that just you have a holdout data for testing, then just you would see a perfect model that basically predicts 100% correct, because you accidentally included both the testing and the training data during the training process. And then just you are using the same data that you used during the training process to test the model, which causes overfitting. And training and testing split is already covered. And typically we use, as we said, 80 to 20 or 70 to 30 split. And the other options that we covered are data transformation, or sometimes, like, just if the data is so unbalanced, special, just across different features, then we may have to center or scale the data using different options. And just the training data, you have a feature, and then just you have a target label. You create this model, and the model will take the future, and in the testing data you don't provide the target label. This is about supervised machine learning. In a supervised machine learning, during the training, you provide both the list of features and the corresponding label. For example, if you are doing image classification, and you have, like, if you are classifying the image of animals, you would have to provide the image with all the details and the name of the animal, the type of animal. It could be dog or cat or any kind of animal. So dog, cat with their corresponding image will be given during the training process. But in the testing process, we want the model to tell us what the image is for, right? So in that case, we don't provide the label, but we simply provide the image, and the model has to tell us what the image is for. So this is in the case of machine learning. In the case of supervised machine learning. In the case of unsupervised machine learning, we won't have even target labels. We are interested to learn more insights, more patterns from the data. So that's just the difference. But this particular diagram refers about a supervised machine learning process where you have both the target label and feature during the training, and then just you hide the target label, and then you provide the features of the data, which just at the end of which you expect the model to tell you what exactly, and then you calculate how much was successful. So that is how you basically calculate the performance of the model. And the cross-validation, that's what we discussed earlier. Cross-validation means during the training process, you would have, for example, k is equal to 1 in the training setup. In the training data, you see, the hyperparameter tuning or retraining process happens within this aspect. You see, like just the lower bar shows you. First, let's say just we have 1, 2, 3, 4, 5 holdouts. We split our training data, our training subset, into 5 different smaller subsets, and 4 of them, as you can see, first we use all these 4 and then just use this one as the testing. All these 4 for training, and the 5th one, the yellow one, as training. And then in the next iteration, we use one. Just this is what shows you the first, the second, the third, and then the 5th will be used for training, and the 4th will be used for testing. And in the third iteration, we will be using the first, the second, as you can see here, but the third will be kept for testing, and the 4th and the 5th will be used. It continues like that. So this is how cross-validation happens. Once we are done with training the data, the model using this approach, then the test portion of the data will be used for evaluating the final selected model and just its performance. And if it gets a good number, a good matrix, then we accept it. if it shows that it is perfect for the training data, not that good for the testing data, that indicates overfitting. Okay, now the first supervised machine learning, the simplest, is linear regression. Linear regression helps us to identify a line that fits a data distribution, a line that basically fits a data distribution. Let me show you here. Here we have points, and then just probably. So here, let's say just we have this point, this point, this point, all these points scattered all over the place. And our ultimate objective is to basically find a line that goes through this, representing a model that fits this. And let's say just this is the line that we have. So this is a simple linear regression line. Simple linear regression. We don't simply draw it. We have to calculate and find what this line is. So this line is. For that calculation, we do this. These green lines are showing just the target line could be this line or this line. But in any case, just let's say this is line one, and this is line two. And the line that we are looking at, the blue line, is line 3. Just to choose among line 1, 2, and 3, we have to calculate. We have to calculate the distance between each point. If this is one of the points, as you can see, this is one of the points, and like from each point to the line, the target line, we calculate the distance. So, and the sum of all these, the sum of all these differences will give us an error. This is how far just this line between the point and the target line or the fit line is an error, because we are finding the perfect fit or the right fit line. So the sum of these errors, errors have to be minimized. The smallest the sum of these errors to a line is the target, or the perfect the line is as, or just the base the line is as a fit as compared to the other. So basically just we try to find the trend line or the base fit, which is with a linear approximation, and very common and intuitive way to explain data in just base fit. That's what we try to find and determine a line that best explains the data and basically minimizes the error between the line and the observation. Just each observation here, the red and the blue line is the target line. Such a blue line that minimizes the error between the individual observation and the target line is a perfect fit, and easy to explain. As you can see, it's easy to explain with how y changes when x changes. For example, just on x and y, as you know, in mathematics, we can simply represent this as y is equal to let's say properly b naught plus b1 x. So this is how we represent this line. And then just our ultimate objective is finding this constant b naught and this slope b1. So this is a simple linear regression, a simple mathematical formula. But y is equal to b naught plus b1 x is a model. It is a model. So we train these using training data, and we also test it using the test data, the test holder. And how do we measure? We basically measure the target y versus the predicted y value will be calculated just to ensure that this constant and this coefficient are the perfect values for our case. And I explained this part in the earlier, but just the simple equation for the line y is equal to beta 1x plus beta naught. Beta naught is the y-intercept. Obviously, from your mathematics, you know that. Beta 1 is the slope of the equation. From this equation, you have like this is a slope, and this is a y-intercept, right? Slope, and this is y-intercept. Y-intercept. And once the parameters are determined, then just you can easily plug in real values, valued x, to get the actual value. And the physical meaning of the parameters are properly explained, and we calculate the value. So we use algorithms, we use code to basically find this. And how can we do a line? As you can see, depending upon, so the simple linear regression has got one dependent variable x and two parameters, which are beta naught and beta 1. Beta 1 is the slope, beta naught is y-intercept. And examples could be the change in GDP or y as a function of changing unemployment rate. If we have just data in Ethiopia about employment versus unemployment, we can basically calculate or create a linear regression representing the GDP change based on unemployment change. Or the heating bill, although this is not common in the case of Ethiopia, but if you have like the electric bill, right? The electric bill as a function of the number of rooms you have in your house, because every room needs a light bulb, and if you have four more light bulbs, then just you would consume more electric power, which results in a more bill. Or if you are renting houses, then just as you have many family members leasing or renting your property, then there is highly likely that most of them would use water for shower, for washing all the clothes of the family members, and then you can calculate the consumption of water by family number. And the height as a function of age, although that doesn't go any further, because at a certain age, height stops, like just height of people stops at a certain age. But you could possibly use at early age, you can use the height of kids or younger people as a function of their age. So this is used in medical institutions, especially pediatricians use these measures just for kids to observe their growth rate as compared to the rest of the population. So they should be here kind of observation. So linear regression gets used in these scenarios. And the other type of regression is a multilinear regression. In the case where you'd have to consider more variables. Now, just here we have one B naught, but there is another x, x1, x2, x3, and it goes on. This is the actual reality, actually. So data doesn't usually come as one. Most of the time, like just your real real-world data set contain multiple features, right? Multiple features. And at times, linear regression or multilinear regression may not represent real-life scenarios. In any case, if you have to use multiple features, then just you would end up creating a multi-linear, multivariate linear regression. And the more general polynomial regression looks like this. In any case, is the dependent variables are raised to higher orders, but still combined linearly. So we call this a multilinear regression. Earlier, we simply saw just a one variable, x, with independent variable, but the dependent variable is y. If the independent variables are more than one, then we call and then just if they are combined in linearly, then just they will be multilinear regression. And you can find this. You can search for this, and you will find it on Wikipedia. So this is from Wikipedia. You can find this Anscombes quartet. We have like just 1, 2, 3, 4 different values. 4 different values for just the same y. Y goes from 4 to 12 in all the cases. But the value of x changes because the value of x changes for different y you would see, right? Or the value of y changes because of the value of x changes. The value of x changes in x1, x2, x3, x4. So these pairs give you different values. What that means is you don't always expect a linear line because you are simply looking at two variables. Because you simply have x and y, you don't assume that just you will always get a linear relationship between such variables. Just you know, right? X and y could create a circle, right? You could use a circle, and their relationship is going to be x squared plus y squared is equal to the radius squared, right? And then just if you have to represent y is equal to x squared, r squared minus x squared in the square root, right? So this is how you would be representing. So the relationship is not in any way a linear relationship. What that means is you have to be very careful. Just every two, like because we have a simple data doesn't mean that just the relationship is simple. The best way is to visualize, use visual technique to check whether or not the variables are related linearly. So lines are not always sufficient. You can always determine a best fit line, but it doesn't always describe the data. Linear regression is simple description of the distribution, not good for complex behaviors. And then just from Anscombes quartet, nearly identical linear fit, but very different descriptions, as you can see. Like just if you add more data, if you are more data, then you would run into issues of your line not fitting at all your data. So it was used to illustrate the importance of plotting the data. So this is important. So you have to plot the data. You have to visualize your data before assuming that the relationship between variables could be linear. And the objective function is a least square error. We want to minimize when we try to create a linear regression. When we try to create a linear regression, let me just avoid this. Let's say just we have these points. We have these points, and we want to create a line. When we try to create a line, just we want to make sure that the error between each point to the line above or below the line gets minimized. That's what we call least square error. We want to minimize the objective function that is the sum of squares of the residuals. These are the residuals. These are the residuals. When they are above, you obviously you would get a positive value. When they are below, you will get when they are below, you will get a positive value. When they are above, you will get a negative value. So it goes like this. So just we want to find the least value, and this is why we do that. The observed value of each, which is this, the observed value of each minus the calculated value, which is the point on the line. A square is what we call, and we calculate this value where y is b1 plus b1x plus b0, and optimize the value of b1, which is the slope, and the value of b0, which is the intercept, that minimize the sum of these squares. So this is the objective. And accuracy, we mentioned that, just we covered it. The accuracy gets calculated based on the observed value and the predicted value. And the error value is observed minus the predicted. And the mean absolute error is calculated as the absolute value of this, the predicted minus the observed. And the mean square error is the square of the value. The root mean square error is a predicted minus the observed. Since this is a square, the order doesn't matter. And so for classification, this is for linear regression or simple linear regression. These metrics are, remember, like just in the course outline, we mentioned some of the metrics that we could use for evaluating model performance. For simple linear regression and for value for models that involve predictions, and the prediction has to be continuous value or real numbers, continuous value, quant valued prediction. We use these numbers. However, for classification, the metrics are different. For classification, we use a matrix called confusion matrix. Confusion matrix. Okay. Now, so how do we measure accuracy? We basically just said that the accuracy gets measured. Again, this is a repetition. We predict on the training data, and we measure the goodness of the fit, on the predicted data. And that is, did the model actually learn what is in the training data? That's how we check in the training data. The training data has got some details that it gives the model, that it trains the model on, and we calculate how much the model learned even using the training data. And the good way, it is a good way to measure if the model is complex enough to learn from the training. And then we use we predict on the test data. Then this is the true measure. This measures the goodness of the model, whether or not the model is actually learning from the training data, but the predicting on the test data is actually the true measure of the model performance. That means, can it apply the learning to new data? This is what is important. This is what's important. Can we, when we use a model on a test data, that means we are simulating the future, simulating the future. Can the model be applicable on a data that it has never seen? So that's what we mean. And it is a good way to measure the model's predictive accuracy in the wild. And the cross-validation accuracy is used for this purpose, cross-validation. Cross-validation means dividing your training data into multiple subsets, right? If you remember from our here. So this is cross-validation. This is cross-validation. The cross-validation applies on this side of the data, on this side. This is the training data, and this is the testing data. This is test, and this is training. The testing data is 20%, the training data is 80%. Then just from 80%, we use cross-validation. For testing, we simply basically just, now at the end of the process, we get the model. At the end of this process, we get the model. And it is the model that gets used here. That gets used. So the cross-validation accuracy is errors during cross-validation, trained on some part of the total training data, tested on the rest, repeated for n different divisions of the training data. But here we measure something in between the training and the test accuracy, and frequently used to quickly measure the model accuracy after training. So this is the testing process. The testing dataset is used to measure the performance of the trained model, And just another approach in supervised machine learning, is using feature selection. Feature subset selection is a process of selecting features, which is typically done in an iterative way. You can either remove one or add one, remove or add one feature at a time, and then evaluate the model performance. Basically, like just for example, in a linear regression, especially when we apply a multivariate linear regression, multivariate means multiple variables of the features. If we have multiple features, we apply we could use multiple features, provided that just the relationship is linear, and then we calculate. And the feature selection means just how many of these features. If let's say just if we have 10 features, how many of these 10 features are important? We either start with 10 and then just subtract one at a time, and another, and then just it goes like this, or from 1 to all the way to 10, and we calculate the performance of the model at every level and just check which feature is important. And there are many standard methods or techniques. And it is basically just there is so much research into this topic, but there is no perfect way of approaching it so far. You can have like the original feature set, and then just you do the subset of you generate subset, and then you do the feature subset used for the evaluation process, and you continuously evaluate. And then if the feature fails, then you change. If the performance is not good, so this iteration goes like this. If the failure is there, but if it succeeds, then you basically just move on, and then you have the selected set of features. So another way is like just sequential selection. You can start with k total features, evaluate each feature separately, and then just build a model with only one feature at a time, and then select the n based features. And so that this is a naive sequential selection, and the possible number of permutation that you can have is n combination k, right? Any combination case. So just you could have this many permutations that you would get, and it assumes the features are completely independent. It's important in machine learning process that you identify whether or not the features are to each other. Otherwise, if one feature is in a certain way related to another feature, for example, the most common relationship is age and date of birth. If you have a data set that contains age and date of birth, then obviously age is calculated based on date of birth. So you have to either take out date of birth or take out age. Given a date, you can calculate age, and then just is the date of birth minus or today's date minus date of birth is age, right? In whatever date given for everybody, this is a formula. So the two features shouldn't be used in training in machine learning training process. This is one particular example. Or if one feature is feature one is equal to a constant k times feature 2, or let's say feature 2 is a certain constant k times feature 1, then just you have to get rid of one of these features because they are perfectly related with a factor with a mathematical constant k. So in real life scenario, many variables interact and depend on each other. So trying to identify someone based on name or city alone versus using both variables, right? So if you are using city, the name of based on name or city, and then just if they are kind of related, you have to get rid of that kind of relationship. And it requires a method that tests all combinations of features. The total of n choosing k combinations is this much. And the other selection is either just going forward or backward. Let's ignore this because I covered it. Going forward means you can iteratively add one feature at a time and evaluate your model or the features in the resulting model. Or going backward means you iteratively remove one feature at a time from the set of features that you already have. And a feature selection, the other technique thing that we said, especially like in this scenario, if two features are related, just like age and date of birth, or one feature is a multiple of another feature, you can quickly find this situation by calculating the Pearson coefficient of correlation. Pearson coefficient of correlation. So this table shows how different features are related to each other. So such a matrix, a correlation matrix, can be generated for features and then just based on values. The Pearson coefficient of correlation just ranges between -1 and 1, and any value, let's say just this is 1 and this is 0 and this is -1. Any value around this or any value around this should be taken. Let's say just this is -0.8, and this is positive 0.8. So if you have correlation coefficient above 0.8 or below negative 0.8, you have to take into account just values close to -1 or values close to 1, values close to -1 from the right or values close to 1 from the left means the two features are correlated to each other. Pearson coefficient of correlation gets calculated for two variables. So for every two variable that we want to calculate, each variable gets calculated or correlated to every other variable. And the diagonal that you see is when the feature is correlated to itself. So this is with itself. Let's say just this is with itself. So the same kind. When a feature is correlated to itself, it is always 1. When a feature is correlated to some other feature that is close to it, closely related to it, you would either get a -1, a value close to -1, or a value close to 1. So you have to get rid of those kind of features. So those are some of the options, again, just that you could utilize for feature selection. Now, the second supervised machine learning model, the second supervised machine learning, which is classification with logistic regression. Now, let's use logistic regression to classify. Before moving on here, do you have any question? Any question? Okay, so there is a question. How can we compare our model during training and testing sets? Well, the process are separate. During testing, during training, you use the data, which let me go back quickly. If you remember this data set here, so this data set, let's say just we have 1,000 records. 1,000 records. From these 1,000 records, we said that 20% of the data is going to be used for testing, 80% of the data is going to be used for training. What that means is from here, 800 of the data for training and 200 of the data for testing. So during the training process, we use this 800, and then just the 800 data will be used, will help us get a model, right? So the model, but the model gets applied on the 200 data. So this is the true testing, a true testing process, a true testing on 200 data, because we have the model at hand, and then we are using the data set that we kept away for testing. But there is also another testing process, which with the 800 data set, especially when we are using cross-validation. When we are using cross-validation during the training process, let's say the data set that we kept for training is divided into 5 pieces, 5 places. So into 5 sets, 5 sets of 150, right? 160. We will have 160 5 data sets. Isn't that right? Which is equal to 800, right? 5 times 0, 5 times 6, 30, 5 times 1. So 800. So now 160 will be kept. The first 160 will be kept. The remaining 640 will be used for the training. And then just 160 will be used for testing. But this is to compare, and just we will have 160 and 640, 5 combinations. And 160, 640, 5 combinations. But these 160 and these 160 dataset are completely different. Each of these 160 dataset, they don't repeat themselves. They don't repeat any of the data points in the 160, don't repeat themselves. What that means is the 640 changes. This is exactly how it is. And this process helps us get better model. Better model, or I would say best model, best model. So this is the cross-validation process. This cross-validation process, this regardless of any type of model training that you use, gets applied. This is a general process. In any case, so the cross-validation process. The cross-validation process, we divided the 800 dataset into 5 splits and just 160 at a time, the 640. So the unseen part. So we are basically switching. So this is 160, 160, 160, 160, and 160 here, right? 160 here. 1, 2, 3, 4, 5. We have 800 data, and this is 200, right? So the total is 1000. Then just we will basically utilize this. Perfect. I hope this answers. And the next question is, what is the technique that are used to solve underfitting and overfitting problems? Perfect. To solve underfitting and overfitting problems, we have to ensure that especially features. The feature selection process is the best solution to avoid underfitting. If we are simply just using all the features, because some features are dependent on others, then just they will give us a wrong impression about the model, a wrong impression about the model. So a proper feature selection, just playing with the features, properly selecting the best features, and also using the scaling technique, data transformation process. The data pre-processing process step will enable us to solve this underfitting and overfitting issues. Why do we cross-validate? Why don't we just use the train test only? Because we want to get the model, a perfect model. So just we are basically calculating, getting the right parameters, the right parameters to get the right data set. I mean the right model, the right model. The cross-validation makes your model stronger, because we are doing mini training test, right? Just before going out with a model that may not properly work with the actual data set. Within the training process, we are doing the training test, just a smaller proportion training test approach. So that's why we need the cross-validation. Okay. Okay. Now, the classification with logistic regression. Now, regression predicts a continuous numeric variable, right? A continuous numeric variable. And for example, just the housing price, customer volume, or temperature. For housing price, we used regression. But classification predicts discrete class. Model learns qualitative labels about the data. Classification is, for example, like just whether or not an image is a dog's image or a cat's image. So this is a dog is a label, a cat is another label, right? Or color classification, red, blue, yellow, of just, so those are classifications. And at times, we may have a binary classification, which is a yes or no, or a one or zero, and discrete disease detection, and a spam filter, like just if an email is a spam or not spam, this is a discrete class. Or a disease detection, whether or not a disease, whether or not someone is positive to a disease or negative to a disease. So this kind of binary classification. Or we could have a multi-class classification, such as closed size, right? Closed size, you will have large, or small, medium, large, extra large. So these are discrete classes. Or image recognition, dog, cat, which we said earlier. So these are classifications. Now, just this is classification, but regression focuses on continuous values, calculating the burn area based on temperature, right? Calculating the today's temperature based on historical temperature, right? Today's temperature based on historical data, which is a number, right? Or calculating the height of a kid based on his or her age, right? So those are kind of regression problem. Continuous variables. Continuous variables are numeric values that can be represented in a real number. Now, for example, this is a tumor size, and this is age. So just this is a kind of classification, and this line shows the classification line. Or we can have a decision boundary, having bigger, having multiple classes, and the classification is the explicit borders to separate the different classes. So these are the classification lines, right? So these line 1, line 2, and line 3 are the classes. So are the classification lines. And the model predicts where the boundaries are. In this scenario, the model tells us where exactly the boundary is. And class membership is most ambiguous at the boundaries. At times, you would see like just some green on the other side, or purple on the green side. Green on the purple, purple, or green on the red, red, or on the, so it's like just the class membership could be. And the model algorithms, there are, in relation to decision boundaries, there are different methods for determining the boundaries. And they differ on the assumption about the data structure and the distribution of the data in the feature space. So when it comes to classification, there are different approaches that we would be using. Linear versus non-linear classification. Look at this. These lines, I mean these points, the stars and the greenish stars, or the red points, are perfectly separated. And it's a matter of calculating the decision boundary as a linear line. and we could easily represent. On the other hand, here we have the star are around the red balls, right? The red balls. So the red balls look like just in a circle. So the decision boundary is a circle, an equation of a circle, right? An equation of a circle. X squared plus y squared plus x squared is equal to c. C potentially being the radius square, right? So, and this is a non-linear decision boundary. Now, in a kind of in binary classification, we have a simplest example. Binary classification uses a single feature. We can, I mean, just in a simplest example, we could use a binary classification using a single feature. For example, predicting the success or failure of a restaurant using the profit margin, right? Using a profit margin. We could use a profit margin, whether or not, just to evaluate whether or not a restaurant succeeds. A basic assumption, the target classes are success is equal to 1 and failure is equal to 0. And at low values of profit, so these are what we are saying, at low values of profit, low likelihood of success. Same thing for high profit, which means high success rate. And the approximate decision boundary at some optimal value of profit theta. So, and then just any value at, let's say, the profit theta, if the profit is greater than this optimal value, then we call it success. If the profit is less than or equal to this optimal theta value, we call it failure. And then just here we go. The profit margin looks like this, right? And we, let's say, just chose this value, right? 4%. 4% as profit margin. Reasonably good model. It captures the general correlation of small error at the extreme values. Somewhere here, it's small, and somewhere here, we were basically able to classify this, right? We were able to somehow classify this. But the question comes when there are values around a certain boundary. So now that we have an ambiguous zone, we have these points like just these points, and we have these points. What are we going to do with this? A linear model is too simple, and it cannot now just they are not properly classified, right? And they need a function that basically outputs only 0 and 1, only 0 and 1. So in this case, linear regression, the simple linear regression doesn't work for us. It doesn't work for us. What we should be doing is this one, a sigmoid function, Now, look here at 4%, at theta is equal to 4%, at theta is equal to 4%, we have this, and then just this function, f of x theta is equal to 1 divided by 1 plus e is a power of negative x plus theta, right? Theta. Now, this negative x is represented by this one. So now we are familiar with this value. Just for simplicity, let's use this as z, and this as z. And z is equal to beta naught plus beta 1 x1 plus beta 2 x2. And it goes on like that. And this is the linear regression, the linear regression. So using a linear regression, but another logit function, then we represented this formula. This actually is a perfect formula, because as the value of x increases or the value of z increases, this value decreases. This 1 over 1 plus e to the power of actually increases, but it goes to only 1 between 0 and 1. With just the high, when the the denominator is so high, then just the 1 divided by infinity. So 1 divided by infinity is equal to 0, right? Or if the sum of these 1 pluses, but the other way is 1 divided by 1. This value could be 1 over infinity too, right? 1 over infinity, because negative x has got a potential to go higher, and then just 1, this term will become 0. This term will become 0 over infinity. When it is infinity, our value is 1. When it is 0, when it is infinity, 1 over 1 plus infinity is equal to 0. 1 over 1 plus 0 is equal to 1. The 0, this value becomes 0 when negative x becomes so high, which makes it a flip of the infinity. In any case, this is the sigmoid or the logit function. In your next advanced machine learning advanced modeling technique for postgraduate students who would be taking that, you will learn this as one of the important functions for machine learning, for advanced machine learning process, especially like just for image classification, for neural network, because this is one of the popular functions. In any case, for us, now we call it the logistic regression. It is a logit function. At the same time, internally it uses a regression formula. So we call it a logistic regression, right? And then just be using theta is equal to 4%. Then just for values here, we have success. For values below theta is equal to 4%, we have a failure, right? So this is success is 1, failure is 0. So the logistic regression can be used like this. And the logistic regression is just one of the probabilistic model. Logistic regression is an example of a probabilistic model, and the output is the probability of the observation belonging to the predicted class, whether it is 0 or 1, either 0% or 100% probability of success in the previous example. And the ambiguous zone is the transition from one class to another, and the probability sharply increases from 0% to 100% near the threshold value. This is what exactly we saw, right? The probability is from 0 to 100%, right? To 1. So this is the probability distribution, And the other probabilistic classifier are naive Bayes classifiers, and we have non-probabilistic classifiers such as that simply determine the decision boundary with no inherent concept of probability. Among them is the support vector machine. Okay, confusion matrix. Now, just in classification, remember, in linear regression, we said that we use mean absolute error, right? The mean square error, or the random mean, the root mean square error. So these are the metrics. the matrix for models, for model performance, right? Now, just these are like for continuous valued uh, models, like for prediction, continuous valued models. We use these, but when we are predicting discrete values like classes, classification, then we have to use confusion matrix. Confusion matrix is used as a way to measure the performance of a classification model, how good the classification model is, how many of the classes are properly classified, rightly classified, and how many of the classes are wrongly classified, how many of the data sets are rightly classified, and how many of the data set are wrongly classified. So this is how we can measure. And as you can see, so the predicted data, let's say just we have 165 data set. And just for a model that we trained, we are using, and then if we have the predicted, and the classes are yes or no in this table, yes and no are the classes, right? Yes and no classes. And how many of yes and how many of no are properly classified. So here on this side, we see actual values. When in the data set, while the actual data is no, the model predicted no for 50 of the points. No actuals were 50 no actuals were predicted as no, but 10 actual no's were predicted as yes. On the other hand, 5 actual yeses are classified as or predicted as no, and 100 actual yeses are predicted as yes. So if you see this, and these are perfectly classified, but we have errors. 5 of actual yeses were predicted as no, and 10 actual no's were predicted as yes. So, and we call these as the actual and predicted as negative, true negative for no's. For yeses, we call them true positive, and positive P, and this is a true positive because the yes are true positive, and the negative, while it is negative, but we said positive, it is false positive. For a negative, we said positive, it is a false positive. For a negative, for a positive, we said negative. This is false negative. For a positive, we said negative. For a positive, for actual yes, we said no, 5 of them. So this is false positive. So this is for a 2x2 confusion matrix, but the classes could be more. And when the classes are more, when you have 3 classes, then just you will have 3x3. 3 classes. 3 classes, the matrix is going to be 3x3. 3x3. 4 classes, and it's going to be 4x4. And somehow a little complicated after that. Most of the time, like just you may not get more than 4 classes in classification. More than 4, but it is possible. It is possible, but you may consider using logistic regression in that scenario because it may not be properly represented. Anyways, so there are other metrics in addition to based on the confusion matrix. Based on this table, we have several metrics that can be calculated from the matrix, sensitivity, specificity, precision, and accuracy. So the classification metrics are calculated as the accuracy, true positive, TP is true positive rate, TN is true negative rate, true positive rate is sensitivity divided by record. The true negative rate is specificity divided by selectivity. The ratio of the negative class that were correctly predicted, and the precision is the ratio of the positive predictions that were correct. So you have this. These formulas can be used, and these formulas are based on this table. Based on this table, you have these formulas. Yeah, and this is a very good graph. You can find it on Wikipedia, and the link is associated here. And the precision, sensitivity, specificity, you can go through these details. And the ROC curve, this is another matrix that you would be using to compare different models. And ROC curve means receiver operating characteristics. Basically, just this ROC curve got its name from the World War II war with the U.S. Army research and its ability of the radar detection of Japanese aircrafts, right? The curve plots and the operator's ability to distinguish planes from false positives, right? Just how correctly the radar was able to detect Japanese aircrafts versus false positive, right? So this is and it is useful for evaluating binary classification classifiers on their ability to find the true positive before detecting false positive. So the curve, the ROC curve, the area under ROC curve is used to measure, and true positive rate versus the false positive rate is a plot of the true positive rate Y versus a false positive rate X. And so this is the false positive rate on the X and the true positive rate on the Y, and then you basically just plot the values. And the data is plotted after sorting by score in descending order, and the score is equal to the probability or the model output. So just read about the ROC curve and you will get a very useful details. And you can compare different models using ROC curve. And the point is ROC curve can be used as a performance metric, and the area under the curve, the larger the area, the better the performance is. Conveniently normalized to 0, 1. If your model is at the top, like the curve associated to your model is at the top, then just the area under the curve becomes larger, and then just the model is somehow better as compared to the other models whose curve is below that particular model's curve. And the random guess results in the diagonal line equally likely to guess either P or N define the worst classifier. So just this diagonal line is the worst classifier. The worst classifier. We don't want a line in between. At least just this is somehow better, and this is by far better, right? Let's say just 1, and 2, and 3. 1 is the worst, 2 is somehow better, 3 is the best as compared, because the area under the curve, is higher for the model that corresponds to line 3. model can recognize more positives before resulting in a false positive. And true positive leads the line more vertical, and false positive leads the line horizontal. So basically, this helps you to compare this is again ROC curve, ROC, the receiver's operator. So the receiver's operating characteristic. And classification with decision trees. I think just let's stop at this point. And if you have any question, I'm exactly at the middle of our discussion, and I'll be finishing this theoretical aspect next week. So let's stop right here, and I will share the slide to you so that you can go through the details at your convenience. Any question? Okay, so okay, so the one question is, what are the main criteria to select the best model to our data set? And can logistic and multiple regression interchangeably? If not, how to differentiate them? Because using y is equal to b naught plus b1x b1 x1 plus b2 x2. Yes, so logistic and logistic and multiple. Logistic regression is usually used for binary selections, for binary. Uh, but linear regression or for linear regression, uh, logistic regression is for binary selection, for binary. So you can split your data into either a 0 or a 1. So that is where logistic regression is used. Logistic regression is used. But if you have a data set that requires and that fits a linear pattern, then a linear regression is a perfect one. When when your data doesn't fit a linear pattern, whether it is using a single variable or multiple variables, you don't have to even use linear regression. Logistic regression is in a situation where you cannot use a linear regression, but your model shows a distribution like this one, right? So for this, you cannot use a line. You cannot use a line. So this is what logistic regression is. But internally, it has got linear regression. This is a linear regression formula. So this one is a linear regression formula. So this is a linear regression formula. And this formula is used in this particular X. So this X is this X. So somehow related, but different. And we are basically just splitting values to this side and to this side. Values to this side are 1, values to this side are 0. We are splitting to a binary 1 or 0 value in case of logistic regression. In case of logistic regression, as you can see here, these are zeros, and here these are ones. Values on this side, because these values are corresponding to this one, and these values are corresponding to this one. Okay. Sorry, I missed the past 10 minutes class due to connection. It's fine. Since class is being recorded, I will share the recording at the end. So just you didn't miss. You will catch up from the recording. What are the best performance evaluation metrics for classification? For classification is classification metrics, right? For classification, we used such a matrix. And as I said, this is for 2 by 2. A 2 by 2 right? A 2 by 2 is for binary classification. Let's say for two classes, let's say 1 or 0, or yes or no, or true or false. So these are for binary. Let's say for 3, if we are classifying color, green, red, yellow, then now for these, we will have a 2 by 2 matrix. For these, we will have a 3 by 3 matrix. And if we have four classes, let's say small, medium, large, extra large, like for close sizes, then we will have a 4 by 4 matrix. So this is what a classification will look like. Okay, so this is what we have for any other question. I can accept one more question. If something is lingering in your mind that needs some clarification, I can provide that. Okay. Any question? Hmm? Okay. If you don't have any question, I think just this is what we have for today. Next week, we will cover classification with decision trees and bring them, just tell your friends that we are covering important aspects. And then just especially the association rules will be interesting because it involves some application in business. And we will also discuss about clustering and the clustering techniques, the unsupervised machine learning. Then just that would be interesting for. So the unsupervised learning will be covered again. Unsupervised learning. So I will be finishing the unsupervised learning next week as part of the classification. So the classification with decision tree, which is related to the supervised model. Once we cover that briefly, the unsupervised machine learning models, especially the a priori classification, the a priori classification, and the unsupervised the clustering techniques will be covered next week. Okay, and next week I will start on time. Please just join as early as you can so that we can utilize our time properly to finish the class in time. Okay, and thank you very much.